Morning, everybody. Thank you for joining us on this quality solutions presentation from Electromechanica. My name is John. I'm the business development manager for our Africa division. So I do all the nice fancy traveling. Arthur will be the power factor specialist. He's our technical manager at Electromechanica. So he'll be doing the presentation. So maybe some house rules. What we've decided is if you've got any questions, maybe leave it to the end of the actual presentation. We're going to keep this presentation short, maybe 45 minutes max. So if you do have any questions, yeah, let's rather wait until the end and just send me put your hands up and we can answer your questions. Or you can email myself, or you can even email Dilip. You've all got Dilip's details. So Dilip will be our contact. So just a brief introduction on Electromechanica. We are a privately owned business, owned by a family. We run about 38 years old. It's been going since the 1980s. We are specialists in automation and electrical products. Generally, we import all our products out of Europe. So we agents for a lot of the big European brands. Some go as far as a 38-year-old relationship. Levata is one of them. Hager is one of them. Then obviously we do have the various brands. So what I will be doing now, I'll be handing over to Arthur. Arthur will be doing the presentation. Please, if we're speaking a little bit maybe too fast, maybe just raise your hand so we can just slow down. But yeah, it's a quick, like I said, it's a quick presentation, not too long. So yeah, enjoy. Thank you.
Thanks, John. Good day, participants. Yeah, as John introduced me, I pretty much focus on the power quality and power factor, which we assemble at our branches here. So let's hit it. The topic of power factor and power quality can get quite deep. We're not going to go all the way into the formulas thereof, but to highlight the concern and a solution to this concern. Okay. All right. John would have sent out the catalogs via digital. Within there, section F is where all the power factor, power quality products reside. So at any point, anything I reference, you will most likely find in that section of the catalog. All right, let's start. Okay, so what we'll do is introduction to power factor, understanding how savings are achieved, try and do an estimated savings, and then a brief view to harmonics. Okay, so where do we start? What is power factor? It's simply a ratio of actual power being used by your circuit, being your internal grid, and normally you will see that as a kilowatt, to the power which is apparently being drawn, which is then displayed as what we call kVA. So everyone uses let's call it the beer analogy. If you have a beer, the useful part, which we refer to as active power here, is the kilowatt. It's the good part, and then the waste would be the foam, and that's what we're referring to as reactive power. On most grids, from the utilities, they will charge you a kilowatt and a kVA. So you will pay for what we call this wasteful foam. All right. The ratio is explained simply by taking kilowatt divided by kVA. A lot of your power meters out there, when you browse the menus, you would see something that refers to PF or COS, and that's what we're going to discuss. So just to get a bit of understanding of what this actually means. So what causes low power factor? So there's two basic categories of loads that we know. Load being on your site, a consumer on your physical site. So there are two typical types. So it's resistive loads. So this can be heaters, ovens, soldering irons. In this case, the current draw, the power, is directly converted into something useful, heat and light. And thus, this is resulting in what we call a kilowatt, which is what we're quite familiar with. So if you see your bills, your utility bill, you would typically see a kilowatt hour, a unit charge per kilowatt hour. Everyone's bill would have that. Okay. Resistive loads are, let's call it pure, and they result in a pure kilowatt reading. Then what causes the bad power factor is what we call inductive loads. So inductive loads would be items such as motors and transformers. So an inductive load requires two kinds of currents. It uses kilowatt to perform the actual work, and then reactive power to sustain the magnetic field. So if we look at this image here on the right, G is my generation, my utility, and then I've got a motor. There are fields within the motor that I need to overcome, which are not seen as useful power, but nonetheless, I need to use power to overcome those magnetic fields in my motor. All right. So that working power to make this motor move is a combination of working power and reactive power, and is referred to as apparent power. And typically, if you look at your utility bills, you would see something that says kVA. So the utility would charge you a unit per kVA or maximum demand. So quite often that happens here, depending on the size of the consumer, they get what we call a maximum demand charge, which could be a type of penalty charge or additional unit charge. So one penalty because you exceeded your demand, your kVA, which is allowed to your site, and then another charge for the units over that. Okay. So what type of loads create this demand or this magnetic field? Induction motors, HID, high intensity discharge light, welding machines, arc induction furnaces, power rectifiers. So this is not a new concept. It's always been there, but the utilities are taking advantage of this. They obviously have to make their money back and claw back your inefficiency. And they do that by charging kVA charges. Now, what you would see, so power factor can be in three different segments. Unity power factor is what we call an ideal circuit. If a circuit was purely resistive, voltage and current would flow in unity, and that's what we refer to a unity power factor. So if I took kilowatt over kVA, that would be equal to 1. So they're in unity. Typically, if you've got a lot of motors and you've got no sort of correction on those motors, you would start getting what we call a lagging power factor. That is when the current is lagging behind the voltage. All right. And this is an inductive load. Okay. This is what we try and fix with power factor correction. Then we have what we call leading power factor. It's not common, but this would be if your circuit becomes too capacitive. You would see this if you had a faulty power factor bank and you go leading. LEDs can sometimes cause a leading power factor, but at a very low current, and so forth. So why should a customer improve their power factor? Firstly, increased energy cost, and this is a direct charge on your bill. So when you look at your utility bill, if you have a maximum demand, it is something you can address immediately. You cannot remove it completely. It will always be there, but you can reduce it and be more efficient. When you reduce your demand, you reduce the overloading on your transformers and the distribution line at the point of injection. Okay, so resulting in less voltage drops and power losses. A good example is at a customer, I think it was in Botswana. He only had a 500 kVA transformer and was fully loaded, so it was stripping out. He had to wait, I don't know how many months to manage with utility to try and get a transformer from council. Now, he couldn't get that going. What he did a recording and said, I'm actually inefficient. I've got a bad power factor. And putting down a power factor system managed to reduce the demand on the transformer enough to prevent tripping out. So without having to change a transformer, much more cost effective with power factor correction, he managed to resolve that problem. All right. Obviously reduces the load handling of the plant because you're overloading the transformers. With the inefficiency, you would have increased penalties for low power factor from utility. And as things start up, as that demand kicks in, if your PF is bad, you would have voltage drops, causing motors to slow down, requiring more current to get the torque to get that load going. So how is power factor corrected? So I referred to COS and PF is kilowatt over kVA. We call this the power triangle. If kVA equals kilowatt, we wouldn't have this COS angle in here. All right. Now we have a little bit of an example. I'm not going to go into the maths here. I had 142 kVA before, and I had a really bad power factor. I introduced a capacitor bank, which reduced the demand at point of injection. So how does this work? On your main bus, you would have a capacitor bank through contactors and the controller sees the requirement and steps in the capacitor bank. Okay. Again, the mag capacity, our beer analogy, my total kVA is my apparent power, and this waste was the reactive. This is what the supplier saw. He saw a reactive and real from the energy supplier, so he charged me on both. I introduced power factor demand, and I brought kVA closer to kilowatts. Okay. So reactive power compensation is done by injecting opposite reactive power in the grid. I'm not going to jump into how the capacitor works and all that, but it creates a phase shift at point of injection. And that is what brings down that demand at point of injection. Okay. This is done by basically introducing capacitors into the network and bringing them in when it is required. Okay, so what we call this reactive power is now coming from the capacitor bank. Okay, so how does a customer improve their power factor? The most practical economic is capacitor banks. Easiest to maintain. It's contactors and caps and a controller. And as the caps steps in, the reactive power is provided in a opposite to the load. Okay, I'm not going to go into the science of this. There are videos that can be found to explain this in more detail. So methods used during application of power factor, there's kind of two ways. I'd like to stick to the image on the right. So I've got my transformer coming in. I've got my connection point, my ACB. I've got my measuring point, which is my current CTs, which is connected to my power factor system. The power factor system is injecting anywhere on that bus bar. So the CTs are monitoring the current flow, the phase angles, and it's telling the controller, hey, I need so much reactive power, so much. And it starts bringing in the banks via contactors. Okay. So where would you install it? It really depends on your problem, but most common is closest to point of coupling with your council, because that would be closest to where you're getting billed from. All right. Some customers may move the PFC system further down into their plant. The reason for that would be is to reduce the demand on cabling. So if you've got a bad power factor in maybe a certain warehouse, which has got some machinery, which is away from the transformer, it may be better to put it there if you're having some cable heating issues due to bad power factor or high demand. Okay, but in most installations, it's as close as possible to coupling of utility. The other way, which is quite an old way, which people do, I don't like it, because you're going to land up having more equipment spread out all over your site, is individual motor compensation. So at your physical motor, the customer would put down a capacitor bank with a contactor. As the motor starts up, if it was on a star delta, when it switches over from star to delta, it would bring in the capacitor. All right, and it would only be compensating at the motor itself. The issue with this is, if anything goes wrong, you can overexcite the motor if a cap stays in, even though the motor is off, and you've got a lot of disparate equipment all over your site at each motor. Personally, do it upstream. Okay. So what to ask your customers, querying for a power factor system, the first thing you need to ask them is, does the customer get charged kVA on their utility bill? First point, before you go any further. Then, does the customer have electrical recordings available of the site? What is that? We use power analyzers. We sell these power analyzers. For me to be able to help you, I need to see a site profile. And we get quite detailed on this. I need a lot more than just volts and amps, because I will be able to identify if there's any other site issues for you. A lot of mistakes customers do make is my network 400? Is it 5 to 5? Is it 690? We need to know this. Does the customer already know his step configuration that he needs? Does the customer have harmonics on their network? Most customers would not know this. You will identify this in the site load profile, which you would do with a power analyzer. All right. So how would our size appear for a customer? As I mentioned before, I would advise putting down a power quality logger. There's a couple of reasons for this, and we'll talk about it once we talk about harmonics. And the logging interval, I would typically ask for around 7 days and 1 to 5 minute intervals on the data points. So what are the data? The peak kVA, the peak kilowatt, the power factor ratio, network voltage, the actual charge from utility, and harmonic levels for voltage and current. The loggers we sell do all this. You can set them down to 1 second, and they will continuously trend on the memory cards for a period. Then once you've recorded, you can share the logging with me, and I can assist you on sizing these systems. Or as you get up to speed, or you may already be up to speed, and then you can already size these systems by yourself. Okay, and then you're welcome to bounce it off me to see if we're all on track. All right. Now, we've spoken about power factor. Okay, before I jump to that, the old way of kind of calculating it was using tables, as you see, like this. It's in our catalog. But I found that, it's a bit cumbersome, and it's not always with you, but there's something that is always with you, and it's your cell phone. And what we've gone and done is we've created a little power factor calculator. It's not an app. It is a link to a website. So what it brings up, if it just wait for it to load up. What I've done for myself, I've just taken the shortcut, and I've saved it as a shortcut on my phone's main page. So when I'm at customers, I can quickly give you an estimate just using this. The formulas behind all this is all very accurate. So it will give you a good average. And I'd like to do a quick example of how I can go about working out how much cable I would need. So using this calculator, and you'll get the link to it. It'll ask you for your basic info, and click start. So what it will need to know is network voltage. I'm going to leave it at 400 amps. the kVA, the maximum kVA that you've seen on the power meter. So let's, for argument's sake, say whatever 500 kilowatt kVA. Okay. Then I will say, what was the power factor that the meter saw at that point in time? So let's say, for argument's sake, it was 0.8. And what would be my target power factor? A good power factor is anything from 0.96 to 0.98. To try and target unity is difficult. It can be done. But there's a lot of things to consider when trying to get to unity to power factor. So we're just going to go to a 0.98. If you got a charge rate, unfortunately, ours only accommodates for the rand. Typical municipalities in South Africa would say 200 rand per kVA. Now click calculate. So based on that charge, my estimated savings, based on that charge, would have been that value. I would have reduced my demand by 92 kVA and reduced the load current by 133 amps by introducing the power factor bank at that point of the peak. So if you look at the existing profile, my existing load in current from 722 to 589. I went from a 0.8 to a 0.98. I went from 500 kVA to 400 kVA. All right. And what did I need to achieve this? I needed 220 kVA of power factor correction. Okay. To do that reduction. Okay. And this is a reduction at point of coupling. Okay. So this calculator is free to use, and you can email the results to yourself. Okay. Again, the important bits would be the actual data you capture. You need this information to start. If a guy gives you a whole lot of motors all over his site, you're going to drastically oversize the system. It would be better to just do a bit of measurement for a couple of days and say, okay, that is what you need at point of coupling. Okay. All right. So that's just to do a basic savings calculation. Then quite a topic now. There's more than one type of power factor. All right. So a normal inductive load is corrected by a normal power factor system. And you got to think of PF in two parts. There's cos phi, and then there's PF. So what we normally know, if you just had a motor on a star delta or a direct online and you were to measure that, you'd be measuring the cos, which some people call DPF or PF. This must not be confused with true power factor. What is true power factor? It's a combination of the cos and what we call distorted power. And that's what we're going to get into now, just briefly on what harmonics are. So harmonics in your system will also affect your true PF. Your council is most likely looking at, depending on the meter, the utility meter, at true PF. So don't make the mistake. A normal power factor system only corrects DPF, cos, not true PF. For that, there's a combination of power factor systems and what we call active harmonic filters, which we'll briefly talk about. Okay. What is the main cause of this distorted power and how is it measured? It basically comes from a variable which we call total harmonic distortion in current. Okay. And this will reduce your true PF. So if we had to relook at that power, the power triangle, we had kilowatts and kVA on a normal system. But true total kVA includes the distorted part of the network. So it's, if we look at fundamental current, is displacement kVA. Total kVA is based, including the IRMS. Okay, this is pretty important because I've had customers that offer a power factor system and say, but we're not getting to that target 0.98. But he's looking at PF 0.98 and not costs. All right, so very, very important. So what creates these harmonics? So our loads have evolved. Before we had direct on lines, then we went star deltas, then we went variable speed drives. So VSDs, switch mode power supplies, computers, archetype lighting, almost anything that's converting AC to DC will affect the power and create a bit of a harmonic. All right, depending on how it's switching, it will affect different harmonic orders within your network. All right, and now I'm going to briefly touch on the subject. It is evolving more and more, but it's something to be aware of, that just because I've gone and put down a drive, or I've just gone to LED lighting, yes, I've reduced kilowatt and I may reduce the demand, but I might be creating another problem. And depending on how much of it I put down into my network, it could result in a bigger problem that results in other failures, which we'll talk about. All right. So it's just an example of different source. So a VSD is, you get 6 pulse, 12 pulse, 18 pulse. The more pulses, obviously the better the drive is, but it's going to cost you a lot more. Typically, it's all 6 pulse VSDs out there. All right. So what causes these? Variable speeds, Thyristor rectifiers, UPSs, all these contribute to a harmonic content within your network. And it's what we refer to as nonlinear loads. And they're typically seen in data centers, process plants, automotive, modern buildings. What do? They create reactive power issue, they create harmonics, and they can create imbalances on your network. Okay, so I'm just going to do a brief example here. This is the interns of a variable speed drive, the very basic interns. I've got power coming in and I've got power going to my motor. But as we know, a variable speed drive has got what we call IGBT. It's got gates, and those gates fire at specific frequencies. And that causes a bit of a, let's call it a clipping on the output power. But that effect is seen on the input power. So it's seen on your internal grid. And I'll run through a quick example of what this would look like. All right. So harmonics may cause system losses, that burden the system. Typical things that can happen, overheating on transformers, decreased kVA, the true bad PF. The big one is the overloading of a neutral. This is typically when you've got switch mode supplies, single phase. A high current harmonic results in a high distorted voltage harmonic, typically. All right. If you had a normal PFC system that's not protected, typically it causes capacitor bank failures, because a capacitor which is not protected will overload and cause breakers tripping, fuses tripping. So in general, depending on how bad it is, how bad the percentage is, it can create other negative effects on your power network. So what I want to go through very briefly is the type of harmonic. We've got what we call a positive, a negative, and a triplet. The positive and the negative, to an extent, cancel each other out. Think of it as how the current moves through the cable, and how that field moves. It's moving forwards and backwards. Some of it doesn't go forwards and backwards. Some of it returns back on the neutral. All right, and that's what we call the triplet harmonic. And those can typically be your worst type. Okay. So a brief view of the different harmonic orders, like I mentioned, positive, negative, and zero. So harmonics in the same direction, positive. These are the harmonic orders. So you got your fundamental 50 hertz, which we all know, and then you got the rest. The negative flowing in the opposite direction, and the zero, which returns basically back on the neutral. Okay. So just to show you what this would look like if you had to see it on a let's call it on a oscilloscope, but this is a very simplified version thereof. You've got a normal AC grid. That's the perfect sine wave at 50 hertz. And basically what that means, the voltage is moving between positive and negative 50 times per second at 50 hertz. The ideal load would have that shape, the voltage. Now, a resistive load would be at unity with the voltage, so current, so the light blue is the current, the dark blue is the voltage, and we're at unity and we're all happy. But this is not the perfect world. What a nonlinear load will do, it will create a square, let's, for argument's sake, call a little bit of a square block on the current within the waveform. All right, and I'll quickly show you what causes this. So nonlinear loads, so like a VSD, does not draw the current perfectly from the grid, so it will deform the waveform on the current. All right. Why does this? A VSD only lets current flow depending on a voltage condition, and it will pulse. And as it pulses, it creates a new waveform, which I'll show you what it could look like. So this waveform is a combination then of all those different frequencies we saw before. So if I had a stable 50 hertz, that would be the first step. We look at that light blue line. Then depending on where the VSD is firing, it either adds and amplifies it. You'll see that yellow now being amplified. And depending on how the harmonic order is triggering, it starts to change that waveform. If you watch the orange waveform. So different steps in the firing of the VSD on the gates or the rectifier creates this, let's call it altered waveform out. Okay. So at the end, you're not left with the perfect waveform anymore. It's got a whole lot of distortion inside. And that distortion inside, that noise, is what we refer to as current harmonics. All right. So in this example, the fundamental at 50 hertz was 75 amps. But because of all the other harmonics that were measured, the total RMS, which includes harmonics, was 86 amps. So you see it actually increased the current which would have been there. And that's not useful. So all frequencies beside the 50 hertz are not useful. You're just going to be charged extra current usage for that. And this is what we refer to as the current harmonic. So it's quite important to know when I'm ramping up the drive or the load, if I have control, what does it do? How much harmonic distortion does it create? Is it a high percentage at a high load? That normally results in other issues. All right. So THDI is the total harmonic distortion in the current. Different recorders might indicate this variable differently, but no matter what, THDI is current harmonic, and then you have THDU, all right, which is voltage harmonic. Now, a voltage harmonic is inherently created by a current harmonic, by your load, because utility says, I'll give you good power. Your current harmonic, if it's bad, and depending on the different orders, returns back to your transformer. Your transformer sees that and returns it back into your internal grid as a voltage harmonic. Okay, So it's a continuous little circle. Sometimes you can get distorted voltage harmonic from your utility or your grid. The only real way to see that is very high-end power analyzers. The simplest way to see it is if you've got a basic power analyzer and your loads are off, but I'm getting a voltage harmonic, you know it's coming from your neighbor. So if you had maybe a neighbor that's got some spot welding and a whole lot of VSDs, irrigation, or you could be next to some massive pumping site that's got a lot of variable speed drives, you might start seeing voltage harmonics coming through and onto your grid. Okay, but inherently it's all caused by a load. So current harmonic is created by the load, causes transformer losses, reduced transformer, cable, tripping, cable life, tripping of breaker. This is obviously depending on how high this current harmonic is. And that results in a voltage distortion at the transformer. Excuse me. This is also an important part to take here is it depends how loaded the transformer is. What capacity is it at? So if it's at 100% capacity and you got all these switch mode supplies downstream, it creates additional stress onto the transformer. Okay. What these harmonics can do is they can affect other equipment because, as I mentioned, the current harmonic results back as a voltage harmonic. Now that is seen by all the other equipment in the field. So a power supply might be seeing this. Another VSD might be seeing it. So there are ways to mitigate this. And as EM, we've got different solutions depending on what the problems are. So if I had to sum up things that can address harmonics, filters, so it doesn't clean the harmonic out, a normal filter or reactor. So on capacitor banks, if you got harmonics, you need to go with capacitor banks that have got tuned reactors to protect the cap. All right. But that protects the power factor system. The other typical one would be an active or passive filter. This is a higher cost system, but it's the ideal solution. An active filter works in real time to counter the harmonic. So it becomes capacitive and inductive in real time. So just an example of an active filter. I've got all my noise downstream, VSDs, LEDs, UPSs. I've put an active filter in line. It measures and it switches to counter those effects. Now, some utilities may have some sort of penalties if you inject high enough harmonics back into the grid. It depends on the council. A good example are solar plants. Inherently, yes, it's clean power, but quite often there will be noise and they will say, if you exceed a certain percentage, you have to clean it out before you give it to me. And the only way to do that would be with active power filters. Okay. How do we know if a customer needs it? Again, we need a load profile, a dedicated logger with power quality logging in. And based on all that, again, kVA, kilowatt, power factor, network voltage and current harmonics per order to be able to determine the size of filters you may need, or you can get away with no filters. You just need to put line reactors on your PF system and so forth. Okay. So that's the brief on just power factor and a bit of a harmonics. Solutions from EM for power factor correction. We've got a full range of controllers. Some are more basic. This is the DCRL range. Depending on how many steps you would need or how many banks, this could be an option. These are typically used for our smaller systems, our wall mount systems. It only needs one CT and it works on two phases, measuring on 2 phases, but it would bring in a 3-phase capacitor. All right. Then the controller up from this, and this is the one I like to use, a DCR-G8. This we do on all our floor standing systems, the much bigger systems. It's a lot more advanced. It's got power analysis built in. It's got what we call master slave. So if you ever exceed the amount of output it's probably the only controller in the market that lets you master slave multiple controllers off one. So we've built cabinets up to 1,600 kVAR. I had to create master slaves just due to the size. That's just an example of what the master slave would look like. And the DCR-G8 is a true complete 3-phase measurement device, preferably 3 CTs to measure each phase, and then it would bring in the steps, let's call it more accurately than a single phase measurement device. There's still a lot of controllers out in the market that just do single phase measurement. I'm not big on that. I would say DCR-G8, 3-phase measurement, so you know exactly what's happening on each phase. It can also be applied on MV solutions. So I would measure on the MV side via VTs, but I would correct on the LV side. Within the PFC systems, obviously we do the contactor. On a normal system, we've got these little blocks with current limiting resistors on. That is to limit the inrush current seen by the contactor. So when you step in that capacitor bank, these resistors limit the inrush current before the contactor sees it. So it's very important to use specific contactors for power factor systems. Okay. Not just, I think it's 50 amps and I just stick a 50 amp contactor in. Make sure you've got product that's got current limiting resistors, especially if you do non-reactive based systems. Then we have another solution. Instead of using contactors, we can do Thyristor switching units. What is that for? The best example would be is spot welding. So the load would come in and out rapidly. A normal contactor-based system cannot keep up with that load. A contactor would come in, go out, and then based on requirements and efficiency, you need to wait about a minute before you bring it back in again. A Thyristor is not like that. It can come in, every couple of seconds, which does a couple of things. It obviously makes it a lot more efficient than a normal contactor-based system. So you'll get closer to your target PF a lot faster. And like a spot welding application where you got rapid switching, the system can keep up with the load. So typical fast switching would be welding machines, pressers, cranes, and so forth. You'd need to rather look at what we call dynamic power factor correction, where we use thyristors instead of contactors to do the switching. So on these type of systems, you're going to have a lot more switching times out of the device versus a contactor. I've seen counters on the DCR-G8 with Thyristor-based systems where they've switched in capacitor banks millions of times already versus something you would not be able to achieve using contactors. All right. A big advantage is that it switches without a transient. How it does that, it makes sure it switches in at what we call the zero crossing of the signal. So it doesn't create any spikes. The controller that's most compatible with this would be the new DCR-G8F, which is specifically built to work with Thyristors. We've got a full range, 400 volt, 480, 690. It would really depend on your application. With NFC support to set up your parameters, any diagnostics you'd need to do, and this would wire back to the DCR-G8 controller. Just a quick view of what I meant by the soft switching. The point of firing would be at the lowest, at the 0 point. So you don't have any spikes or little interruptions, transients on your voltage. Okay. We only use electronicon capacitors in our systems. They do not have any liquids. They have a harmless neutral gas, which is nitrogen. High safety, self-healing with a safety release. What is self-healing? It's just to do with the dielectrics inside it. As you got little transients that occur in the cap, the material inside closes off after the little short circuit has occurred. All right. The protection system, they call it the BAM. As a capacitor sees too many voltages or issues or overloads, it does build up pressure internally, and instead of just rupturing, it will release itself and will disconnect itself from the network. A typical capacitor should have over 150,000 hours worth of life. It's all dependent on how well you're protecting that capacitor. If you don't put line reactors on and you've got a lot of harmonics, your capacitors will not last. They will blow out, they will fail. So historically, people are quite scared of PFC systems. They have had fires before. Historically, manufacturers used plastic casings. They've moved away from plastic. They've moved to steel. On these type of systems, I haven't had any fires. Plastic, yes, there's been fires. It happens because the wear and tear, internal disconnection doesn't work properly. It fails. The unit ignites internally and starts melting. Okay. We also do a full range of detuned reactors. What is a reactor? It looks like that, and it's wired in series with a capacitor. So we've got a range from 400 volts to 550 volts. So we can design a system around those network conditions. Then for power factor, for power quality, we can do capacitor banks, but it is limited, slow response. We do what we call static VAR generators, which are dynamic. These will do power factor correction, leading and lagging in less than 1 millisecond. And then what I mentioned earlier, active power filters, and those are specific to clean out harmonics on your grid. Again, it's depending on the cabinet size, it will come onto your grid, it would measure your load, and you can grow these cabinets to quite big sizes to do the filtering. What we've got a brochure which highlights our solutions. Give me a sec here. Okay, if you can see the screen, can you see the screen with the brochure? Okay, so we've got this brochure which gives you a very brief intro to power factor, a link to our calculator for you to use, the same one which I referred to earlier, brief overview of harmonics and solutions thereof, what our systems would look like. This is a typical floor standing non-reactor, showing you all the components that are used within this. Serviceable components. So any one of these racks could be removed, replaced with another. Contactors can obviously be replaced, fuses and so forth. Yeah, so these floor standing units are physically assembled here in our Sandton branch by our workshop. Customers could buy complete systems. You tell me I can go any size pretty much, or customers would just buy the racks from us. So we do racks that are non-reactor. You'll see they're a little bit smaller. So that's just fuse holder, contactor, cap. Then we do what we call detuned reactor based. So as before, that line reactor is wired in series with the cap to protect the caps. Now, depending on your network, harmonic, if you've got high levels of 5th and 7th is what we typically see, you would go over what we call a 7% detuned capacitor bank. If you had high third orders, you'd go over 14%. Okay. This is just some examples of the floor standings that we build. We're not limited to. We try and keep to the step configuration, but we can obviously build much bigger systems for you. And then what we have, we've got the reactor-based systems, but you will get this brochure, so you can go through it at your own time. And then we do a small series of wall mount systems where you may have a small farm somewhere. The guy's got some basic issues, doesn't have any drives on his farm, and he says, can you help me out? I've got bad PF. The council is hitting me on the power factor side. There is these sort of solutions. Note that these solutions are for indoor applications. We have been requested for outdoor applications. It's a little bit complex because of the amount of heating that can happen internally in this. Means these systems vent quite a lot of air. That's not easy to do just by placing this unit outside. Customers that would want outdoor mounted units would need to then buy their own racks, their controller, and build their own systems based on their own designs. This is the tool I use, the PAL 103. We use this for our recordings. The suitcase comes with your Rogowskis, your coils to do the current measurements, clamps for voltage, and a little power adapter, so it powers the recorder off the bus bar. That's for up to, let's call it 400 volt networks. And then part of the maintenance tools would be also maybe looking at some sort of cameras to invest any hotspots and so forth. We also have a comprehensive user manual, which we supply with each system. We can share this document with you. And it's got certain guidelines with regards to commissioning, maintenance involved in these systems. So you don't just install and you walk away. You have to go back. You have to go check every couple of months. Has the load changed? Because quite often what happens is a consultant designs this for an empty warehouse. It says, I need 300 kV. System is installed. The occupant of the warehouse comes. He puts down a whole lot of VSDs, maybe a furnace, all sorts of things. Now the system is undersized or not protected properly. So you identify this within your maintenance, that the load hasn't changed considerably. He's not introduced other factors in that negatively affect the power factor system. So the maintenance guide is to show you how to install it, a wall and a floor standing system. And then it's got a basic maintenance log, what to measure on the cap, see if the cap has deteriorated, do I need to replace the capacitors? Okay. Another critical component for power factor system is the CT. The CT is separate because we don't know the size of your breaker or your cables. You have to select the CT accordingly. I like using split core CTs, obviously on existing infrastructure. If you got a 2,500 amp breaker, you don't feel like disconnecting all the bus bar work. You can clip in these split core CTs, which we also sell. So we have a dedicated page, as you'll see if you go to www.em.co.za. You go to solutions, you go to power quality solutions. This brings up our main landing page. What is power factor? It's a brief little video of what we've just discussed. Our calculator, our brochure, and then just direct links to the different types of systems that we build. That is me briefly. I know it was a lot of info in a short period. And I think we can see if there's some questions, and let's get John linked back in. Thank you.
Yes, also thank you. It was a lot of information, but like I said on the little chat that I put out through, We're more than happy to send you through the PFC guide, the actual PFC catalog, also linked to the calculator, which will assist them. If you guys have any questions, you can just send me a message and I'll check with Arthur for the response. Any questions, any information you require, additional information? I hope it was clear. It was, yeah, it was as much as we can do with the side of the times being everything online at the moment. I see Arthur has also posted his email address. You can email him directly for questions, technical questions, technical support. More than happy to help.
If anyone wants to ask a question later, you can drop me on an email. Try and put on the communication, just so we always know where it's coming from. Again, if you're not familiar with the topic, there's a lot of videos out there, but no, there is solutions from us. We could do custom builds according to your requirements. A lot of our systems going to what we call our SADC regions, and more the utilities are pushing for this with all the different power problems that are going on. They're looking at ways of charging the consumer, not just kilowatts, but kVA. One topic I didn't speak, and I just want to quickly touch on it, is if you're looking at solar systems and your site has got bad power factor, my strong suggestion, first sort out your power factor. First improve your inefficiencies before you go solar. What the most solar guys do not understand power factor, and the power you're generating because of your inefficiencies is going towards losses. So what you thought you were going to get is not 100% there. So power factor normally improves that ROI if you've got bad power factor. So the ROI of solar and PF together will be faster. Okay.
Okay, perfect. Thanks, Arthur. If there's no questions, we get a sign off. I would like to say, obviously, thank you guys for taking the time to join us on this webinar. There's been 7 attendees, so thank you for your time again, and we will probably have more and more of these in the future, more dedicated to a specific field. But then obviously we will deal with the DLIP. There is someone's put up their hand, Mr. Eddie. What is your question, sir?
I'm gonna just click allow to talk. Just give me a sec. Eddie, can you see if we can speak?
Okay, can you hear me now?
Yeah.
I was struggling to get my microphone on. Can you hear me?
Yes.
Okay, so thank you for this webinar. So I'm Eddie, working for Kamoto Copper Company as an electrical project engineer. So I do have a question regarding the effective way of correcting the power factor. Is it by filtering the specific harmonics or by just generating your own reactive power, I mean megavar to the capacitors? So what is in between both? What is the best or the effective way of correcting power factor?
It really depends on your site. So you'd have to first do some basic logging to determine what is worse. Because if you've got really bad harmonics, a normal power factor system is not going to work for you. Then you're going to have to look at the harmonic side of it. But I can use an example. I had a customer with a basic crusher, conveyor belts, just on not even soft starters, star deltas. In his scenario, most economic, best bang best money spent was just capacitor banks. Okay, but he didn't have harmonics. And he reduced stress on his transformer. But now if I use that same example and I said he, instead of using star deltas, he just put VSDs everywhere, which he reduced his demand, which I'll agree to, but now has created another problem, which is now affecting maybe he had a solar plant. Now the solar plant keeps disconnecting because of bad harmonics.
By the harmonics, yeah.
Yeah, then you got to go and look at active harmonic filtering and try and bring it as close as possible to the load that's creating that problem where possible. I've also seen scenarios due to bad harmonics, gensets not wanting to synchronize back. So it's quite a one. You will need to have some sort of power quality logger. Establish at first point of coupling. Is it bad there? Where are we sitting, and which load is creating the biggest problem? Because you might just need to sort that specific load out. Maybe you've got a chiller plant, and that in itself is creating an internal problem on harmonics. So it is a little bit of investigation. You do need the tool to do it. So there's not an answer for everything. You'd have to do a bit of a measurement to see what is worst and what is contributing the most. But I can use the example again with the gensets. Customer has only got gensets. He's got a solar plant and he's got a lot of drives, and now nothing wants to work. His generator doesn't want to sync properly. The PV keeps disconnecting, but the guy that did the VSDs, he's happy because he sold a lot of VSDs and everything is working. But now he's created this other problem. Now, what you need to do then is get to those drives. Do they have line reactors? Do they have chokes? Do they have front ends? Or do they have nothing? Then you got to say, okay, well, we need to look at active filtering at point of coupling to those drives. And that may be enough then to lower the harmonic to make the solar system work fine and no issues with the generator. Okay. There's not an answer that I can tell you which is best at this stage. You have to do a log to see.
Okay, so thank you for answering. So yeah, okay.
Okay. If you have a site that you have a bit of an issue, you can email us, John and I. Let's see what we can help.
Okay, no problem. I will do so. If there is any need for me to do that, I will do. Don't worry.
Okay. Thank you. Thank you for the question.
Okay, sir. Thank you.
Thank you.
Any other questions? If no other questions, then we'll log off now. I've sent you again my email address. I've sent Arthur's email address. We will send you information on our guide, our PLC manual, and also on our loggers, just for your information. And yes, again, thank you for your time, and thank you for spending some time with us. And again, have a good day, and yes, stay safe, I think is the word. So thank you very much.
Wow. Thanks, guys. Bye. Bye.